The indefinite integral. Like I said, you are going to be able to apply anti-differentiation to the indefinite integral. Anti-differentiation, you know what differentiation is. That's the process of taking the derivative. So now we're doing the anti-differentiation process, which is the opposite. I'm just going to jump straight into it because we've already done the whole, limit process, which is how to actually figure out what the derivative was, that foundational concept of calculus. Integration, I'm just jumping into it. This is how you find the antiderivative of a power function, okay? This would pretty much be considered like the power rule of integration, okay? It is 1 over n plus 1 x to the n plus 1 plus c, okay? That's how you find the antiderivative of x to the n, any type of power function where c is some arbitrary constant and n does not equal -1. If n did equal -1, then we of course would have a 0 exponent. We would have 1 over 0, which we cannot have. Okay, so n can never be -1. So what that looks like in its most basic and its most simplest form. If you're like now, what you basically are going to be given is you're going to be given the derivative, okay? So let's say the derivative ended up being x squared. Now, using the antiderivative, you are going to basically be able to find the original function now. And to do that, you would use this rule. So it would be 1 over n plus 1. Well, if n is 2, 1 over n plus 1 becomes 1 over 2 plus 1, which is 1 over 3. So it's going to be 1 over 3 x to the n plus 1. So then that's going to be to the third power plus c. That is going to be your original function where c is an arbitrary constant. Okay? This is how you find the antiderivative of any power function. You can always check your antiderivative, your original function, by taking the derivative of f of x to see if you do indeed get the derivative. And as we know, we bring down the exponent, subtract 1, and that is how we get x squared. Okay? The derivative of constant is always 0, but you need to make sure that you include that plus c. So we're going to find the antiderivative of each of these functions, okay? I'm going to do this one with you, then there's going to be some that you're going to do on your own, okay? So when I find the antiderivative, remember, I add 1 to the exponent. So when I add 1 to the exponent, I get what? $11. And then in the front, it's going to be 1 over that new exponent. Then you have your plus c. And that is the antiderivative of x to the 10th power. For b, I have 1 over x to the 5th. Well, the only way I can use that power rule for indefinite integrals is I need it to be in the form of x to the n power. So that means I need to rewrite 1 over x to the 5th as x to the -5. Using your laws of exponents, you can bring that exponent up to the numerator, and now I can apply that rule. So I'm going to add 1 to my exponent. So -5 plus 1 is -4. So then my new exponent is going to be -4. My coefficient is 1 over -4. We'll have our plus c. But of course, we cannot work with any negative exponents, so we need to bring that x to the -4 back down to the denominator. So my final answer is -1/4 x to the 4th plus c with that x to the 4th in the denominator with the 4.
Would the 1/4 be 1/5?
No. Remember, whatever your new exponent is, that is the denominator of that coefficient. So when we add 1 first, and then that becomes the denominator of that coefficient. For C, in order to use that power rule, we can't have it in its radical form. We have to turn it into an exponent. So this becomes x to the what power? 3/4. Hence that skill from your do now this earlier. So I need to add 1 to my exponent. What's 3/4 plus 1? 7/4. That's my new exponent. The coefficient is going to be 1 over that new exponent plus c. Now, you know good and well we cannot have a fraction within a fraction, which is what we have right now, that 1 over 7/4. So how do I simplify 1 over 7/4? I got to keep change flip. So I'm going to keep the 1, change the division to multiplication, and then flip that 7/4 to get 4/7. So then my coefficient actually is going to be 4/7 x to the 7/4 plus c. And that is the antiderivative of c.
So it's okay that we leave.
So I want you to try these 6 on your own. I want you to try these 6 on your own. All right, so my antiderivative for x to the 7th is going to be 1 over 8 x to the 8th plus c. Remember, you add 1, and then you divide. Then your coefficient is 1 over that new exponent. Here, when you add 1, this will give you x to the -1, and then 1 over -1. But you can't have a negative in the exponent. So then our final answer is -1 over x plus c. Here, when we add 1, we will get 4/3. That would technically be 1 over 4/3, but we cannot have a fraction within a fraction. So it'll be 3/4 x to the 1/3 plus c. And if you recognize, 3 and 4 were the same thing. So yes, even for number 4, it was 3/4 x to the 4/3 plus c. I forgot to make that into a 4 in number 3. For 5, hopefully you turned it into a rational exponent and you brought it up out of the denominator. So then that way, when you added 1, you ended up getting 1/3. And then your coefficient in the front was 1 over 1/3, but you have to keep change flip. So that'd be 3x to the 1/3 plus c. And then last but not least, when you bring this one up out of the denominator and you add 1, and then you divide, or not divide, but your coefficient is 1 over that new exponent, you have to make sure to turn that exponent back to a positive. The entire fraction is negative, and never, ever, ever forget your plus c when you're doing anti-differentiation, or sorry, the indefinite integral. Okay? Never forget your plus c on the indefinite integral. Now, anti-differentiation, like I said, is known as the indefinite integral. Is known as indefinite integration, and it can also be denoted, besides just saying anti-differentiate, it can be denoted with the integral symbol. The black symbol is the integral symbol, and then that stands for the indefinite integral. The dx that's beside that integral symbol is like the notation that goes along with it, okay? You cannot have an integral symbol without having dx or dt or dy. Basically, it's that notation that goes along with the integral symbol, and then the x could be a different variable. It just depends on what the variable is of the function that you're dealing with. So for example, you see the integral of x to the 3rd dx. Remember, the integral symbol and the dx always go together. So when you see that, they're always together. So then that would indicate find the indefinite integral. And you see that'll be 1/4 x to the 4th plus c. Another way to represent basically going backwards, doing the indefinite integral. Let's say if capital F prime of x equals f of x, then we write the integral of that function, dx, and it would equal basically the antiderivative or the indefinite integral plus c. Remember, c is the constant of integration. The slide is basically the proper notation of how you can write an indefinite integral. So like I said at the very beginning of this lesson, anti-differentiation is going backwards now. So it's like now when we're given a function, that technically represents the derivative, and we're trying to find the original function. So this right here, that's beside the integral symbol, is technically the derivative. So when you do the differentiation of that, you get the original function. Sometimes it can be represented with the capital F if the function on the inside is represented as f of x, but a majority of the time it will be written as f prime of x, and then you're finding the antiderivative of that, which would then just be f of x plus c. That's just enough. This up here is just another way to represent the original function. Here are some of your basic rules to find indefinite integrals. Okay, the very first one you guys have already written down. This is again known as your power rule for indefinite integrals. So you have the integral of x to the n dx, like we just practiced. That's 1/n plus 1 times x to the n plus 1 plus c. Of course, n cannot equal a -1. You have your constant rule, which basically says if you take the integral of the constant k dx, then your antiderivative would be kx plus c. Okay? Remember, it's like we're going backwards. So anytime you have a constant, the antiderivative of that is just the constant times x. And then of course your plus c. For your constant multiple rule, anytime there's a number in front of your function and you're taking the integral of that, what you can do is you can pull out that constant and then do the antiderivative of the function and then just multiply by k afterwards, whatever that constant is. And then you have your sum or difference rule, very similar to how it was for derivatives. When you're finding the integral of basically an expression, so you have multiple pieces, you're basically doing the antiderivative of each individual piece. So let's say that you have this function written in the pink, the integral of 4x to the 3rd plus x minus 3 dx. This is a combination of all these rules put into one. First, you have your sum and difference rule, because what you need to do is you basically need to take the antiderivative of every single piece of that expression, okay? For that first piece, this is basically the constant multiple rule. So you could pull out the constant and then just find the antiderivative of x to the 3rd, which we know is going to be 1/4 x to the 4th. And then we just have to multiply it by the constant that we pulled out. So then that becomes what? What's 4 times 1/4?
1.
1. So then we'll have x to the 4th. Over here, the integral of x dx, well, that applies our power rule because the exponent here is a 1. So then what's the antiderivative of x?
One half x squared.
1/2 x squared. So then that'll be the next piece of this. And then the last one is our constant rule. Remember, anytime you take the integral of a constant, it's just the constant times x. So then this just becomes a negative 3x. And we cannot forget our plus c because we are doing the indefinite integral. And this would be our answer. We can always check it by doing the derivative of this function, which remember, you bring down the exponent, subtract 1. So we would get 4x to the third. When I bring down the 2, multiplied by 1/2 gives me 1. So that's how I get x. And then negative 3. Derivative of constant is always 0. That's how you can apply all these rules in one particular function. So let's take a few minutes. Probably going to put 6 minutes up again. And I want you to find the indefinite integral of each one of these functions. So we should have gotten, for A, we should have gotten 1/7x to the 7th plus c. That's your very basic power rule. Here you should have got 4t plus c. Do be aware, variable does matter. So if it's dt for the integral, you want to make sure that your variable is a t. For this one, you should have gotten 3. You should have gotten, what you got to say? 1/2 x to the 6th plus c.
You can put an extra 6 over 2.
Or you can say x to the 6th over 2 plus c. Yes, they both do work. Remember, this one you can pull out that constant, then it'll be 1/6 x to the 6th. Then you multiply, that's how you get 1/2. Over here, you guys said this one was 3/5 u to the 5th plus 2 u to the 3rd plus 2u plus c. Yes, wonderful. That was the constant multiple one and the sum and difference one. And then over here, we should have gotten 1/2 x squared plus 3/4 x to the 4/3 plus c, right? Yeah, wonderful. So we can take this and basically know that we're finding a general solution. Okay, anytime you have a plus c, that's known as a general solution. The c does matter when you're given other pieces of information. Just up to this point, you've just been practicing how to find the indefinite integral, okay? But now you can find a particular solution when you're given a boundary condition. So let's say that you were given this integral of 2t plus 1 dt, and you found the integral to be t squared plus t plus c. Well, what if you were also basically told that this represented a particle and the position at time t equals 1 is 6? Okay, if you recall from the derivatives unit, position is the original function of a particle, okay? Position, also known as displacement, was the original function. So when it says that time t equals 1 is 6, it's basically giving you a point on your original function. That point being 1, 6. So when you're at 1 second, you are 6 meters away or whatever. You can use that point to find the value of c by plugging in that point and finding out what the constant is. And by doing that, you do find a particular solution, in this case to represent this particle, that was at 6 meters after 1 second. At that point, you no longer have a plus c, but you actually have a value for your constant. And that happens when you're given a boundary condition within your problem. So here's an example. If f prime of x equals 3x squared plus 2x, and f of 2 equals -3, we need to find f of x. Remember, f of x represents our original function. F prime of x represents our derivative. So to find our original function, again, we're going backwards. The process of going backwards is finding, or is integration, okay? So we need to basically take the antiderivative of derivative, which is 3x squared plus 2x. So using what we know and how we've been practicing today to do that, what is the antiderivative of 3x squared?
X cubed.
It'll be x cubed. What's the antiderivative of 2x? X squared. And then we'll have our plus c. This is the general solution for f of x. But since I'm told that f of 2 is equal to -3, I can actually evaluate for the to find the value of c. I know that f of 2 is equal to -3, and if I plug in 2 for every x, I'll get 8 plus 4 plus c, and I can continue to solve for c to find that constant, and then also find my particular equation. 8 plus 4 is 12. When I subtract, c is equal to -15. So my function that has that as the derivative with the point 2, -3 being on the function is x to the third plus x squared minus 15. And that's how we can use anti-differentiation to find the original function. Questions? We'll look at two more. The curve y equals f of x passes through the point 32, 30. The gradient of the curve is given by f prime of x equals 1 over the 5th root of x to the third. Don't forget, gradient of the curve means the derivative. Don't forget about that notation. So in order to find my original function, I need to do the antiderivative of that function. Go ahead and find the antiderivative of 1 over the 5th root of x to the third. When someone has it, let me know. 5 over 2 x to the 2/5 plus c. Is that what you said? So that's my general solution. But I'm looking for the particular one to represent f of x. So I'm given this point that's on the actual curve of f of x, so that means I need to plug in. I'm going to plug in 32 for my x. I'm going to set it equal to 30, and I'm going to solve for c. Again, here comes that skill from the do now to try to simplify this. This is not a calculator. What is 32 to the 2/5?
4.
It is 4. Remember, that's basically saying the 5th root of 32 squared. The 5th root of 32 is 2. 2 squared is 4. So this becomes 5 over 2 times 4 plus c. What's 5 over 2 times 4?
10.
10. So when I solve, c is equal to 20. So my function that has the gradient of the curve given by the that derivative and passes through the point 3230 is 5 over 2x to the 2/5 plus 20. Last one. So in this problem, it says the rate of growth of a population of fish is given by dp over dt equals 150 square root of t. For t is greater than 0, but less than or equal to 5 years. The initial population was 200 fish. Find the number of fish at t equals 4 years. Remember, when you see the rate of growth, the rate of increase, that indicates the derivative, hence dp over dt. The change in your population over the change in time is given to you by this function. Then we're told that the initial population was 200. The initial population would indicate that's when time is equal to what? 0. So we basically have a point 0 to 100 that is on my original function. That point is going to help me find c after I take the antiderivative of the rate of growth equation. Then to find my number of fish at 4 years, all I have to do is, once I have my general equation, plug in 4 for t. So I do need to take the antiderivative of 150 t to the 1/2 dt. I'm going to go ahead and change that square root into the rational exponent that I need to use. Now I need to take my antiderivative of 150t to the 1/2. When you have it, say it out loud. Very good. 100 t, make sure it's t, to 3/2, and then of course r plus c. This represents our population equation, but a general one. Specifically, I need to figure out what is the full equation so that way I can find the number of fish at t equals 4 years. So I'm going to use that point, and I'm going to plug in 200 for my population and 0 for my time, because remember, initial means at the very start. So that's why t is 0. Of course, 0 raised to any power is 0. 0 times 100 is 0. So my constant is going to be 200. The equation that represents the population is P of t equals 100 t to the 3/2 plus 200. Now all I need to do to find my number of fish after 4 years is plug in 4 for t and solve. Go ahead and do that and tell me how many fish I have after 4 years. 1,000. Because 4 to the 3/2, that's taking the square root of 4 to the 3rd power. Your do now problem, multiply by 100, add 200. And that is how we use and apply the indefinite integral. Okay? Don't forget, the integral symbol implies antidifferentiation. Remember, it's always paired with this dt or its dx. They always go together when you write it. Don't forget that. Anytime you find a general solution, you always must have your plus c. But if you're finding a particular solution, you take the point that's given in some shape, way, or form, and you plug that in to find your specific or your particular solution.